right, time for lesson 6-6. This is Mrs. Trombley coming at you with exponential decay. We've talked about exponential functions in general, exponential growth, and now decay. What is exponential decay? Well, it occurs when a quantity decreases by the same factor over equal intervals of time. So growth is when it's increasing by the same factor, and decay is when it's decreasing by the same factor. We've actually seen some examples already of decay, we just didn't classify it as that yet. So a function in the form of, remember when we learned about exponential growth, we had this whole 1 plus the r? Well, this time we're subtracting the r from 1. So it's kind of opposite, and decay and growth are opposite, so that's good. So in this, the a has to be greater than 0, otherwise everything would be 0. And r, the r is going to be between 0 and 1. So greater than 0 but less than 1, we're dealing with a fraction or a decimal. That's how you could recognize it as decay, because when you multiply by an amount that is between 0 and 1, or sorry, greater than 0 but less than 1, we're getting something smaller. Okay, so same exact equation. We have our final amount. We have the initial amount that we start with. The r is still the rate of decay. It's going to be given to you as a percent. Divide it by 100 to make it a decimal. We have the t for time. This whole amount here is kind of like your b. It's the decay factor. The whole amount is the decay factor. So your steps to this, and you'll see, are you take the rate that's given, the percent, you change it to a decimal, and then you subtract it from 1. There's a reason why we're doing that, just like there was with the other one, and I gave you the example of the sales tax. So now we're going to talk about, instead of paying tax, we're going to talk about something being on sale, which is far better. So a certain pair of jeans you've had your eyes on, they cost $48 normally, and you saw a sign, they're on sale for 20% off. How much are they on sale for? And I wrote before tax because some people will get confused about should we include that or not, and I'm just letting you know you don't have to. Now, most of the time, if you're out and about and you're trying to figure out off 20% off, I'm quite certain that the normal thing you would do is you say, okay, well, 48 times, and you take that 20% and change it to a decimal, 0.2. And when you do that, you get $9.60. Now that's the amount of money you get off, right? So now you have to go ahead and you have to say, okay, well, what is 48 minus $9.60? And if you have your calculator handy and you type that all in, we're going to see that those jeans are now $38.40. So that was 2 steps, right? Well, up here it says that you can just take 1 minus the r. So watch this. If I take my r, that 20% divided by 100, you get 0.2. If you take 1 minus that, you get 8/10, right? So now take 48 and multiply it, instead of 2/10, multiply it by 8/10 and see what you get. Yes, when you do that, you get $38.40. And the reason this works is because you're paying for 80% of the item. If it's 20% off, you're still paying for 80% of it, right? So 48 times the 80% of the 48, that's how you get $38.40. So if you just multiplied a by the rate, you'd only be getting the amount off. I want y to equal my new amount, so I have to make sure to include the other portion of it, because the 20% is what we're not paying for, the 80% is what we are paying for. Hopefully that makes sense. If it doesn't, we can talk about it more tomorrow, that's fine. But again, I don't want you just memorizing rules. When do I subtract r? When am I supposed to add the 1? I want you to understand what you're doing, so you don't have to think about it too much. It's not a rule you're memorizing, you just know it. Alright, so our first goal for today, of course, it's tables. I want you to be able to identify exponential growth and decay from a table. So remember, if the quantity decreases by the same factor, we're dealing with decay. If it increases by the same factor, we're dealing with, if it increases, we're dealing with growth. And remember, with exponential growth, it was greater than 1, right? But with decay, it's going to be greater than 0 but less than 1. So that's really what we're looking at here. Okay, so here's the table. I'll stop all this small talk here. Speaking of small, I know these tables are kind of little. I'll zoom in so we can see it a little bit better. Okay, so we're trying to determine growth or decay. I see that this is going up by 1 every single time. And here, I'm going from 270 to 90, 90 to 30, 30 to 10. I see that that's not a constant rate of change, not a number that I'm adding. So what I want to know is 270 times what is 90? And like I said before, if you can't look at that and know, then take 90 and divide it by 270. Now when you take 90 divided by 270, you get 3/10 repeating, right? So you can either write 3/10 repeating, or you could write 1/3. I'm going to write 1/3. I like that because that's exact. So if you take 270 and you multiply it by 1/3, you get 90. And if you take 90 and multiply that by 1/3, right? Because 90 divided by 3, same thing. You'll get 30. And if you take 30 and multiply it by 1/3 or divide it by 3, you get 10. Do you see how the growth factor right here is a number that is greater than 0 but less than 1? Because this number is greater than 0 but less than 1, that means that this is exponential decay. Alright, and we know that because b is less than 1. Maybe I'll say that. It's all kind of crunched in there, but you know what I mean. Here, I'll box it. Box it out. Make like a basketball player and box out. My husband would appreciate that. Alright, maybe some of you will too. Next one, I'm sure you're thinking, oh, these values are going up. This is exponential growth. Just bear with me here. 0 to 1, 1 to 2, 2 to 3, yes, up by 1 every time. Well, 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40. We're multiplying by 2 every single time. This is growth. It's growth because b is greater than 0. Alright, so the amount that you get for b, our factor, is greater than 0. We didn't have to worry about percents at all, right? Because you weren't given any percents at all in this. This is just, how can you recognize growth and decay? Look at what the factor is. If the factor is between, or greater than 0, less than 1, it's decay. If the growth factor is greater than 0, you're dealing with growth. Alright. Next, I want you to be able to interpret an exponential decay function. Doesn't that sound like fun? So what are you doing Friday night? Well, I'm going to interpret some exponential decay functions. What are you doing? Yeah, I know. Sorry, I'll stop. No, I won't. I can't promise that. I don't know that I can. The function p equals 4,870 times the quantity of 94 hundredths to the t power represents the population p of a town after t years. I don't know that I'd want to go to a town that has a population of p. That just sounds disgusting, but maybe people go there. They really have to go there. By what percent does the population decrease each year? I'm not asking you to plug any values in for t. I'm actually asking you what percent the population decreases. So if you recall from the exponential growth, when we had to figure out the growth percentage, we looked at this, and didn't we kind of undo what we did to it to put it in there? Okay, so the first thing that we did before was we took away that 1 that we had added, right? Well, now this time we took 1, and let's see, we're supposed to subtract that from it. So here's what you're going to do. We're going to take 1 and subtract that amount from it so we can get what we started with. When you do that, this is what you get, right? You get 600ths. Okay, once you have that, I want to know the percent. So before, when we plugged percentages in, we had to divide by 100 to get the percent out. I'm going to multiply by 100. So the answer to this question is 6%. So to undo this when it's decay, and how will you recognize it, that it's a decay function and that you're supposed to take it away from the 1? Well, see how this number in here is greater than 0 but less than 1? That's how you know. This represents the b. That's how you know this is decay. So that's where this comes into play. It's a rhyme. I'm a poet and I didn't know it. Alright, the next question says, a function a equals 275 times the quantity of 9/10 to the t power represents the area A in square miles of a coral reef after t years. By what percent does the area of the coral reef decrease each year? So I'm asking you by what percent. That means I need to undo what's going on in here, right? So to get this, we need to subtract 9/10 from 1. Well, 10/10, because that's what this really is, minus 9/10 gives me 1/10, right? I have 1/10, and you might be thinking, well, what are we supposed to do with that? Well, when you got 0.06 here, didn't you multiply it by 100? You're going to do the same thing. You're going to take 1/10 and multiply it by 100. And if that's confusing for you, isn't 1/10 the same as that? I just left it as a fraction. Those mean the same thing. That's how you say it, 1/10. So maybe that's a little less confusing. Both of them equal 10%. So if I ask you what's the percent, you're looking at the B. You subtract it from 1 and then multiply by 100 to undo what you did up here when we put it in there in the first place. All right, turn your page, and we're almost done. I need to find my second page. There it is. Okay, applications. We're going to talk about cars. And that's kind of exciting for some of you, I bet. Not too far away, a couple more years you'll be driving, and you will find out that the value of cars is really exponential decay. It decreases. The second you drive that car off the lot, it's so sad, but true. Okay, the value of a car is $21,500. It loses 12% of its value every single year. So the fact that it's losing a percent, decreasing by an amount, that represents decay, and it's decreasing by a percent, that's how I know, okay, I have to use that weird formula instead of just being given the B. Okay, A, write a function that represents the value y in dollars of the car after t years. So, I know it's going to be y equals, we're going to take the initial value, that's always A, right? Well, initially this car was worth $21,500. In order to figure out the B here, you are supposed to take the percent that's given, so I'm going to write that over here, divide it by 100 to make it a decimal. That's what you get, right? We get 12 hundredths, and now to figure out what to put inside there, I'm going to subtract it from 1. Don't do it the other way around. You're going to get a negative number, and that will be very strange. So when you take 1 minus 12 hundredths, you end up getting, I know that I could do that in my head, but I want to make sure I'm appropriately giving you the time. Do you have it yet? I hope so. We get 88 hundredths, and it's going to be to the t power. Voila, there's your equation. So this will tell me after any number of years how much that car is going to be worth. And letter B, I want to know, okay, you drive this car for 6 years, how much is it worth? So you paid $21,500 for this car, and I want to know after 6 years how much you can put it on Craigslist for. Well, 6 years, that's time, that's what you're going to plug in for t. So this total amount that the car is worth, I have to take 21,500, multiply that by 88 hundredths to the 6th power. When you do that, and I'll type it in, I've already got the answer in front of me, but I'm going to do it anyhow just to make sure I'm giving you enough time. Make sure that you are always typing things in and not just waiting. When you do that, it doesn't just come out automatically dollars and cents. Comes out to this value that you think, maybe that can't be right. A $21,000 car, and now it's worth under $10,000. That is right. That's what happens with cars. The thing I want to talk about is to make sure that you stop this amount at the hundredths place, because that's money. Money stops there with the cents. The number next to the hundredths place is 5 or more, so that means I'm going to round this to 69 cents instead of 68. So the car is worth $9,984.69. Sad but true. This is what happens. And that's only if it's in great condition. I know. They're expensive. Alright, a lovely little science application is next. And you don't have to know just yet what these terms mean. Just know they're very scientific. Magnesium-27. And what's that, you say? It's an isotope of the element magnesium. Is it clear now? Okay. It decays. So, decay. I know I'm using that 1 minus equation. At a rate of 7% per minute. Alright. Suppose a sample contains 30 milligrams of magnesium-27 at 1 p.m. Okay, don't be thrown off by the 27 here. That's just part of its name. right? Letter A. Write a function that represents the amount of magnesium-27 present after t minutes. So now our time is in minutes. That's okay. It doesn't have to be days or years. It's minutes. So y equals, this is an exponential decay function. You already have the template on the front page of what it's supposed to look like. A is supposed to be my initial amount. Do you remember what my initial sample is? It's not 27. It's not 7%. It says the sample contains 30 milligrams. So that's my initial amount, right? I'm supposed to multiply that by 1 minus the decay rate as a decimal. So the decay rate is given as 7%. So I need to change that into a decimal. And then I subtract it from 1. So when you do that, that's what I'm doing here to get this thing, you get 93 hundredths, and I want a general function. I want just a rule, so I'm going to leave this as t for time. If you're in the habit of putting a little x there, I would not mark you wrong for that, but it does say after t minutes, so technically you should have t. I pity the fool that doesn't read the t. Okay, sorry. Am I sorry? Do you really think I'm sorry for that one? If you know me, you know that I'm probably not. Alright, anyway, how much magnesium-27 was present at 1:15? Okay, I'm not going to type in 1.15. This is one of those where it's kind of like the years. We had 1980, and then it was 1985, and what was it then? It said up here that we started this at 1 p.m. Well, now, it's 1:15, right? And t represents minutes, right? Because it says after t minutes. So, from 1 to 1:15, how many minutes have passed? Don't you wish they were all like this? Yes, 15 minutes have passed. So I just need to go back to my equation that we just wrote and plug in 15. So we started off, the sample was 30. We had 30 milligrams. Plug it all in. I'm going to do it too, so I give you enough time. I know, I say that every time. I can't help it. I'm just passing the time by. When I type it in, I get this. You don't have to write the whole thing. I think that hundredths place sounds good. Why not? So we have this, and then the number next to the hundredths place is 1, so that means I'm going to leave it like it is. So it's 10 and 10 hundredths, and these are milligrams that we're dealing with. That's what the problem says. So I'm going to write mg for milligrams. That's it for exponential decay. I'll see you tomorrow.